Okay, everyone. Okay, so I'm trying to re-record what we missed today. And let me bring up the slides first. It might go quicker than the actual class, but we should be able to cover the material just as fine. So let's see. Yeah, so I'm trying to re-record the first, only the first 60 minutes material, probably going to be shorter than that. And I will try to bring up all of the questions people have asked in class so far. Okay, so let's see. I think we did a quick review of the problem that we are looking at. So this is a teenagers and televisions example. And we, in particular, were trying to use a binomial model for the particular situation. However, just like last time we talked in class, there are a few things that we need to make sure that is not being violated, especially if you're trying to put a binomial model. You're making the four assumptions, right? You need to, first of all, have only binary outcome. So success or failure. It is satisfied over here because if we define having a television to be a success, then for this case, each of the sample teenagers can only have either have the a television or not. So it's either success or failure. The second assumption or condition here is that all of the samples should be independent. Okay? So here, the independent assumption is saying that one teenager having television does not affect the other or another teenager having a television or not. So this independence assumption, as we talked about last time, can be questionable, okay? Because we don't know how the samples are collected. So even though they were talking about randomly selected, might still be saying like a group, a particular area of kids going to have a higher probability of having a television than the other, and maybe they're dependent from each other. So this is one of the assumptions that might be violated or questioned. The third one, I think, is the fixed number of like total number of experiments or total number of sample. So in this case, it is okay because we know that you're given a particular 1,048 sample teenagers. And the last one is sorry, maybe that's just my alarm, same success probability across all of the samples. So this might be, I guess, another questionable assumption over here, because we actually don't know whether there will be the same or not. Again, maybe social economic different situation over there. You might have one group of kids having higher probability of the other group having a TV in their room. So these are the four assumptions where you're doing a binomial model. The second and the fourth might be questionable, and the first and third are satisfied. So in this case, we're going to proceed with the binomial model anyway. But again, I want to emphasize that we always need to be sure certain conditions that we're making when we're putting a binomial or any kind of data model out there. All right, so what we did, we also just looked at the binomial model really quick again. So it's independent Bernoulli trials. So for this is 0 or 1. And then the success probability is theta. So the PDF here is success probability raised to xi, and failure probability raised to 1 minus xi. So because xi is either 0 or 1. If its success is 1, then it's theta. If it's 0, then it's 1 minus theta, which makes sense. So for the binomial, it's sum of independent Bernoulli trials. So y is the random variable for the binomial. It's telling you the number of successes. And you know that because xi's are binaries, yes or no, 0 or 1, row 1, 0. So the number of success y will just be sum of all of the xi. In the end, we define y given theta to be a binomial model. So again, theta is the only random thing here. Remember earlier we talked about for binomial model, the number of samples are fixed. Its total number of trials is fixed. So the only thing that is random is the theta. So the probability, the density, PDF of y given theta will be n choose y, success probability theta raised to the power of success, number of successes, and failure probability 1 minus theta raised to m minus y, which is the number of failures. So pay attention here, y, which is the number of successes, can only be integer numbers, and it starts from 0 and ends at n. It can be 0 success and can be at most n successes. Okay, and then the expectation and the variance of this binomial model, and the R functions associated with it. So you see that D norm, D by norm, P by norm, Q by norm, and R by norm. So you see this D, P, Q, R. Just like in the homework question from homework 1, question 4. In my demo, I did D norm. And some of you, if you're trying to answer the second part of the question by generating normal random draws, then you probably have done R norm. And of course, with the D logis and maybe R logis. Okay, so you will see that it's very common to use this set of functions: density, percentile, quantile, and random. Okay, so a lot of the known density, a lot of the known distributions, R has certain packages out there available for you to evaluate the density, evaluating the percentile, evaluating the quantile, and random draws from the distribution. So this can become very handy as we go along the way in this semester. All right, so now we're gonna look at how to make inference about theta, which is the success probability, and we're gonna use Bayes' rule. Okay, so this is what we know before. Okay, nothing new here. Posterior theta given y is the ratio of prior multiplied with the likelihood divided by the marginal density of the data. However, in this particular example, the binomial case, the marginal density of the data can be further explicitly written in this way. So first of all, this is, again, a review of probability. If you have the joint of the data and the parameter, if you integrate out the parameter, you're going to have the marginal of the data. Okay, so this is what we have. And I want to draw your attention to the range of this integral. So usually, generically, we write a indefinite integral. Okay? However, here we're doing a definite integral from 0 to 1, and it is this particular range because theta is a success probability, okay? It's between 0 and 1. So over here, we can write very explicitly that it's from 0 and 1, okay, and d theta, okay? So this is the marginal density of the data, and right now, we're gonna all assume that, okay, so earlier in class, we talked about for the Bayesian paradigm, you assume that the data, which is y, is fixed because that's all the data you have, and parameter, which is theta, is random. Okay? So for now, I want you to be convinced that even though we don't know what exactly the marginal density of y is, it's something known. We just unfortunately do not know about it at the moment. But because it's a given number, it's a constant, so a lot of times we don't have to worry about what is in the bottom. Okay, so instead of doing this inequality, we can write proportional, and we get rid of the marginal density of y in the bottom. So here, the posterior will be proportional. Here, posterior is proportional to the prior multiplies with the likelihood. Okay, so here we write as subject to a normalizing constant to unit integral, and this normalizing is from py. Okay, so this is what we're gonna start with, and later in the lecture, I will show you actually for the binomial case when you have certain set of prior distribution that you're using, you can actually evaluate what that PY is, and you're going to come to the same conclusion. So right now, we're going to assume that we don't worry about this PY. We're just looking at the proportional sign and then try to identify what the posterior distribution would be. And later, we're going to derive exactly, even if we care about PY, we are still able to derive what the posterior distribution is, and they're the same, okay, with or without looking at this. So for now, let's not worry about the normalizing constant and just focus on prior for theta, data model for y given theta, and then try to recognize what the posterior distribution it is. Okay. All right. So prior specification. So this is the first step before seeing any data. You will try to put a prior distribution described by this py over here, p theta over here. Okay. So before, so earlier in the first lecture, or the first introduction lecture, we talked about the example of finding the proportion of Vassar students actually going to put all-nighter last semester to get work done. So over there, remember we came up with the prior by asking everybody's opinion. So like you can choose from 11 different choices, 0.0, 0.1, 0.2, etc. until 1.0. So you got 11 options over there, and we count how many people vote for what, and then construct a prior over there. So that is a discrete prior. And that, as far as I can remember, I think the majority of you chose between, so either 0.1 or 0.2. So it is kind of like a subjective prior in the sense that you might know, say like when I ask you about it, you might know, you might have a educated guess because you know other Vassar students, including yourself as well, and you will be able to make a guess of what the true probability or percentage would be. However, when situations arises where you actually don't know what the prior distribution might be, you might just put a very uninformative prior. So over here, it's a uniform density. I'm writing here as a common default choice. Over here, default choice, meaning that if you don't know anything better, how about just make the prior, because it's a probability, so let's just make it equally likely from 0 to 1, and that will be a uniform distribution. So a quick review over here, if theta follows a uniform distribution, and let's just do A to B, then the density of theta, this is a continuous uniform, so it will be 1 over B minus A. Okay, so B minus A is pretty much like the length, and then you're dividing one with that in order to get the PDF. Okay, so for our case, because we're dealing with a probability, so we're gonna do uniform between 0 and 1. Okay, so that means we have a density equals to 1. So this is what this is about. Okay, and it's a flat density, each point equally weighted. All right, so this is a default prior, default choice as a uniform density. And this is the case where it is very uninformative because it's just telling you that it can be anything from 0 to 1. Okay, so the thing is, if you don't know anything better, you might just put an uninformative prior because you want to let the data to decide what the posterior will be. Otherwise, if you know, say, if you know a lot of Vassar students and you already asked them before and you already get an educated guess of 20% of them actually going to stay up one night last semester or last academic year, then you might want to put a different prior. It's going to be different from a uniform because now you might want to have a peak around 20%, and you might want to put a lot of probability density over there just to represent that you're actually making an informative prior. But for now, let's just look at uniform, in particular uniform in the context of having like the proportion of having televisions at home. All right, so the results of uniform prior, let me slow down over here a little bit. So you notice that if I'm doing a posterior, what do we have before? It's theta given y, posterior. We're only looking at proportional because we don't worry about the marginal density of the data, py at the moment. So you have p theta, that's the prior, multiplies with the likelihood. So what do you have? Because now we're doing proportional, okay? And the thing that we care about is theta. So anything from the prior and the likelihood, anything in these functions, anything not related to theta, I can actually put it into the proportional sign because it's a constant. Okay, so that is why, so p theta over here, we know that it's a uniform, so it's 1. And for the likelihood, we know that it's n choose y, theta raised to the power of y, and 1 minus theta raised to n minus y. Okay, and you notice that here I wrote a proportional, and I even got rid of this choose function because n choose y has nothing to do with theta. All right, so if you do that, you notice that it's py, a theta given y, proportional to theta raised to the power of y, 1 minus theta raised to the power of n minus y, and this is what you have. And notice that I write in this special way. So even though it's theta raised to the power of y, I write it as y plus 1 minus 1. And over here, it's power of n minus y, but I'm writing as n minus y plus 1 minus 1. Okay, I will explain in a minute why I'm doing this, but I want to convince you, make sure that you know how this algebra is doing over here. Okay, so now I want to tell you, the reason why I write in this way is to help you to recognize it to be a beta distribution. So in the next few slides, we're gonna introduce more about this beta distribution. But for now, I want to tell you that as long as you see a form like this, like theta raised to some power, and then 1 minus theta raised to some other power, if you rewrite the power into something minus 1, something minus 1, you'll be able to recognize it to be a beta distribution. So the first parameter for this case will be y plus 1, and the second parameter will be n minus y plus 1. Okay, so this is the reason why we write plus 1 minus 1 even though it's 0, but we're rewriting this way in order to recognize the hyperparameters of the beta distribution. And the beta distribution for this for any beta, maybe let me write beta, 2 parameters a and b. This is the PDF. Okay, so you have some gamma function defining this way, but mostly we're dealing with integer. And if you know x is integer, then gamma x is x minus 1 factorial. Okay, and theta raised to a minus 1, 1 minus theta raised to power of b minus 1. So in class, Katie and Eli, they both asked the question as follows. So from here, we know that. I'm just rewriting it and highlight down over here. This is not that different from the binomial, right? In fact, because we are putting a uniform prior, this is exactly what we get from the binomial. Remember the binomial? N theta. So density of y given theta will be n choose y, theta y, 1 minus theta, n minus y. Right? So this is what we had. And if you ignore the normal, like a constant over here, this is exactly what we have over here. So the question raised up by Katie and Eli was, why don't we use a binomial distribution for theta? Okay? Why it is not a binomial distribution? Why we need to learn about this beta distribution? So I guess in class I rambled around a little bit, but now because I'm redoing it, I have a better idea and a better way to answer it more efficiently. So the gist of this is, okay, here we're looking at the posterior, okay? And posterior of theta, which is the parameter given the data. So if you look at this, in terms of theta, it is the beta distribution. But over here for the binomial model, it is in terms of y. Okay? So if it is a function in terms of y, and if you see this, you will know that that is a binomial. However, if you're curious about the distribution of theta, it's not a binomial. It's the new distribution that we're learning right now. It's called beta. Okay? So the biggest distinction is binomial here is for the function of y, while beta is for the function of theta. Okay, so, but I think it's a great observation that this binomial and beta, they're so similar to each other. In fact, in this lecture, not today, but next lecture, we're going to learn that binomial, if you have a binomial data model, if you have a beta prior, you're going to arrive at a different beta distribution, which is the posterior. So beta binomial is a class of well-studied prior data model. So if you start with the prior as beta, if you get the data as the binomial model, you're going to arrive at a different beta. So let me write beta 1 and beta 2. Okay, and this will be a posterior for a theta. And for this class of prior distribution, we call them conjugate priors. Okay, conjugate priors, meaning that if I start with a class of prior, here beta distribution, and I combine with the data, I arrive again at a beta distribution, even though different, but it's still from the same class. So if you see this kind of pair, it is conjugate prior. Okay, so we'll spend more time on like talking about the definition and look at some other examples of prior, conjugate prior. But the short story here is, if you're looking at beta, you start with the beta, you end with the beta. If you end with the beta, and if we know very well about this beta distribution, you know, for example, earlier we looked at how you can use D in R, I mean in D, P, Q, and R. All of these functions exist for beta as well. So if I know exactly the hyperparameters for the beta distribution, I know everything about the posterior. Okay, I don't even need to make simulations. I can actually compute exact numbers as I want, and then I can summarize this posterior distribution very carefully. So this is the appealing feature of the conjugate prior example, in particular with the beta binomial beta. And later I will give, soon I will give more examples of what this means. But for this particular slide, it's telling you that, okay, if you start with a uniform prior, you're looking at binomial data, you're going to arrive at a beta posterior. Okay? And the appealing feature is you know what exact distribution it is that you are able to summarize about the posterior distribution of this theta. All right, so what does it mean? Let me bring back the data that we have. So we have 1,048 observations, like samples, and out of them we have 692 successes. Okay, so based on what we have over here, so Y is 692, N is 1048, and we know this result if we put, so first of all, make sure that it's under the uniform prior. The posterior distribution we are able to compute. It's going to be, so this is the A, and this is the B. A is 693, and B is 357. Okay, so earlier I was talking to you that in R, you can use D beta, R beta, etc., etc. So once we know the exact posterior distribution, we can make summary about this. So let me give you some example. So in R, you can use D, P, Q, R, all of this function, and they all exist for beta distribution as well. Okay? So I'm using the quantile function over here in particular. So that's Q, stands for quantile, Q beta. I'm returning, so first of all, this is a string. I'm returning the 0.025 percentile, the median, and the 97.5 percentile. And you notice that for these two, these are the endpoints of a 95% credible interval. So don't worry about the term for the moment, but in Bayesian analysis, we call those intervals, we don't call it confidence intervals, we mostly call it credible interval. And the correct way, so you see that it's 0.63 to 0.688. So the interpretation of this confidence intervals, the credible interval is that we have 95% chance that the true percentage of teenagers having a television in their room is 95, it's between 63.1% and 68.8%. And the median of that probability is 66%. All right, so in the Q beta function, you're also fitting what is your A and what is your B. Okay, and because from this particular example, we know exactly what they are, so we can actually very exactly, explicitly show you what would be a 95% credible interval and what would be a median over here. And of course, you can return other quantiles, percentiles, etc., as you like. But this might be something, might be what people mostly interested in. So I return them over here. Okay, and also I plot the prior and the posterior on the same plot. So let's look at this together. Again, I'm doing this with 3 lines. And the 3 lines, hopefully you find them very familiar now, especially after finishing homework 1 with the R demo that I posted and explained in a short video. So first of all, I'm generating a lot of values, incrementing by 0.001, and I start from almost 0 to 1. Okay, I'm doing from 0 to 1 because it's a distribution about theta. Okay, and theta, the range is from 0 to 1. Okay, so the plot function, I'm actually using the d beta, so you might find this familiar as well. I'm evaluating the density of the beta distribution with y plus 1 and n minus y plus 1. So this is my posterior. Okay. And here, d beta, I'm using 1, 1. So something important to know that uniform 0 to 1 is the same as beta 1, 1. Okay. So you can also write like d unif, I guess 1, 1 as well, that's fine. But here I'm using it consistently, just trying to use the fact that uniform 0, 1 is the same as beta 1, 1. So you can guess this will be the prior. Okay. So here I'm using lines, and I think you can also use point. That's the example that I used, the sample code. But they're doing the same thing. They're on top of the existing plot that I had before and overlaying another plot. Okay. So this is the plot over here, okay? And you notice that the dashed line is for the prior and it's flat. It's from 0 to 1 and it's at 1 over here. And the posterior has some very interesting shape. It's very concentrated at this point, okay? And I think in the class I asked the question, what is this number? And Grant, the remote student from Harvard, volunteered to be about 0.66. And this, if we get back to compute what the data tells us, so the data, the ratio, the sample ratio is n over y over n. I think it's 692 over 1048. It is very close to, I think just a few more decimal points. It's about 66.1, something like that. Okay? So if you have taken, so you notice that the posterior is concentrated around the sample proportion from the data. So if you have taken mathematical statistics courses like that, you will know that this is the maximum likelihood estimate. Okay, this is the MLE for a proportion. And this together with how close the posterior mode is telling us that if you put a very diffuse prior, sorry, maybe earlier I didn't define diffuse. So diffuse, meaning that it is very uninformative, just like the uniform prior that we have over here. If you don't know anything better about what the prior should be, so why not just put a diffuse or uninformative prior like the uniform over here? And if you do that, it's not that you're making a bad decision. You're actually letting the data to drag the inference from the posterior. So like this case, the peak, the mode of the posterior is very similar to the MLE from the data. And that's not surprising because you put a very diffuse, uninformative, flat prior for the theta, and you let the data drag the inference. Okay? All right, so this is just another way to summarize what you have got from your inference. And let me introduce you more about this beta distribution for a little bit. Okay, so beta distribution is for theta. So the random variable is theta, is for theta from 0, 1. And beta distribution has only two hyperparameters. So here I use hyperparameters because theta is a parameter for the model. And then the distribution of theta, now we're learning this beta distribution. And beta distribution itself has parameters. So we're gonna call this hyperparameters. Okay, they're just like one layer lower. So beta distribution has two hyperparameters, A and B. Earlier, I think in class, Sereni asked the question, what are A and B? So for example, for normal, we know that normal distribution has two parameters, okay, mu and sigma squared. Okay, one is related to mean, the other one is related to the variance. So for beta distribution, if you know what A and B are, you know uniquely what the beta distribution is. So beta AB uniquely define what beta distribution is. So you need to know what A and B are in order to know what beta distribution you're working with. So the PDF is a continuous distribution, and the PDF is 1 over the beta function. So again, beta function, you saw this before. It's ratio of gamma functions. Don't worry too much about this. We learned about if A is integer, then the gamma function A is A minus 1 factorial. So you'll be able to compute this, and it's a constant, okay, as long as you know what A and B are, it's constant. And the second half of this PDF is theta raised to the power of A minus 1, and 1 minus theta raised to the power of B minus 1. Okay, and we know the mean and the variance in terms of A and B. The variance is kind of hard to see the effects of A and B, but if you focus on the expectation of the beta distribution, you know that the larger the A, the higher the larger the expectation will be. The smaller the A is, the smaller the expectation would be. So you can imagine how you can play with A and B in order to represent a different probability that you have. Say for a success probability, I think, just like the percentage of Vassar students gonna work overnight last academic year, I guess to represent what we as a class thought about the problem, I think a lot of people chose 10% or 20%. So that means that we should choose a smaller A comparing to B, okay? In order to represent, say, just for the mean, for example, how big the probability should be, because it's around 20%, which is closer to the 0 than comparing to 1. So that means you should have a smaller A than B, and you're gonna adjust how it is to represent the mean. And of course, you can also keep playing with A and B to represent how variable or how much variability you want to put for this particular success probability. Okay, so okay, so don't worry too much about what it is, because in the next slide, I will introduce you different choices for A and B and how the beta distribution is going to change based on different A and B. All right, and I think this is actually the last slide that I just realized that I forgot to hit record. All right, so shapes of beta prior. So here I plotted 9 different beta distributions for you. And what we looked so far is beta 1, 1. Remember, I said beta 1, 1 is uniform 0 to 1. Okay, you notice that the shape of this distribution is flat, okay, from 0 to 1, and p theta is 1. And this is representing a flat prior. This is representing that I don't know better about anything, so I'm just gonna decide that I'm gonna put a uniform prior from 0 to 1, any probability is equally likely. So okay, so I think in class, we looked at a couple of other prior distribution, looking at the shape. What does those prior distribution tell us? So let me talk about this one first. Okay. This one, I picked this one at the beginning to talk about in class, because I think, you see, like the shape is kind of bell curve, but it's not symmetric, and it's centered, or not centered, I mean like the mode. Most of the probably mass is around like, so here is 0.6, so it's about like 0.7. So this will be a good prior distribution for someone who believes that the success probability is about 70%, but it's very widespread, okay? That person might still believe that it can have a large variability in terms of what the prior that I would put on. But overall, it's going to be a prior. So this is beta for 2, A is 4, B is 2. This distribution, by plotting it, you can see that it's around, is center, not center, it's the probability mass, the mode is around 70%, and it's still widely spread. Okay? And I think in class, Katie offered some insight of understanding this prior. So this one is beta 0.5, 0.5, A is 0.5, B is 0.5. And this can be a very good choice for someone who has a belief like this. So notice that here, the density is almost like 0 in the middle, right? But it's high on the top, and it's symmetric. So for someone who believes that, okay, for this entire group of teenagers, I think there are 2 distinct groups out there. One of the group is having a very low probability, so this would be this one, and the other group will be having this probability very high. Okay? And these 2 groups, because if you look at the plot, it's symmetric, right? It's like a bowl, but symmetric, and very low probability at the middle. So this can represent the belief that there are 2 distinct groups. They're very different from each other. One is having a high probability, one is having a low probability, but I think there are 2 groups, so I'm gonna put a prior like that. So beta 0.5, 0.5 gonna help you with that, if that's what your prior belief is. Okay? And of course, you can see there are so many other choices over here, but I think the last set of examples that I circled out is this 2. And both of these 2 are decreasing, right? You see the trend, but they have different ways of decreasing. This is like linear, okay, sharp decrease across time, linear. And this is slowly decreasing over here. So both of this are representing some higher probability for the lower end, but they also represent the belief that, okay, as theta gets larger and larger, I think it's less likely. But for beta 1, 2, I think it's less likely more quickly. While for beta 0.25, 0.52, it's going to decrease, but less quickly. Okay, so of course, I mean, you can also keep comparing this 2. You can compare the other 2s here and this 2s here and there. Up to you. But I just want to use this set of 9 plots over here to show that, okay, if I know about this beta prior, if I know, maybe let me say, if I know about beta distribution, and if I know only, as long as I know A and B, because that's the only 2 hyperparameters for this beta distribution. If I know what A is, what B is, I can actually play around with this and then to choose a prior that can represent more of what I believe, okay? So if you don't know anything better, choose the uniform. If you believe there are 2 distinct groups, choose this one. And then if you think, okay, I think it's about 70%, but I still think it's widely spread out, then I'm gonna choose this one. And many others, okay? So this actually gives us the freedom, because if we're actually gonna put a distribution, a whole known distribution for the unknown parameter, we can do many things. And beta is a very widely used prior choice for the binomial distribution. All right, and I think then, yeah, I'm gonna end here because the second part of this video, which is about, I guess, 18 minutes, is showing you the remaining part of this lecture. Okay, all right, thank you guys. So let me know if you have any questions, and see you later.